Okay, in this lecture we're going to talk about shearing stresses. And before we get into those details, let's just review for a minute or two what we know about axial normal stresses. So here we are with the bar in tension. We have an axial force, a force that goes through all the centroids of all the cross sections down the length of this bar. And we know that we can calculate the stress, the axial normal stress, is the axial force divided by the area of the cross section. And with that, we get a uniform stress distribution. That's our assumption. And we talked about how that was a good assumption for axial normal stresses when you have an axial loading situation. Well, now we're going to take a look at a different loading mode. And instead of the force coming perpendicular to the cross section, if we apply a force parallel to the plane of the cross section, we can have a shear force. And I've labeled this F shear. Now, to keep this in equilibrium, I really do need to look at just a very small length of material. In fact, this length, delta x, approaching 0, so that we don't get any force couple situation going on to keep this thing in equilibrium. We're going to relax that and show you how to deal with that in just a few minutes. But for right now, we're going to take a look at the stress distribution that we get when we apply a formula very similar to what we had for our axial normal stress. We can apply the average shearing stress formula is equal to the force in shear divided by the area in shear. So stress is force divided by area. And our axial normal stress, we have an axial force divided by the area of the cross section. For the shearing stress, we have the shear force divided by the area of the cross section. Now, I did label this as an average shearing stress, and that's kind of an important thing to note. With this formula comes an assumption that we have a uniform stress distribution, just like we did up here in tension. Now, the force in tension, the arrows go down the axis of the bar for the stresses. Because the force is pointing downward, the distribution shows a downward directed shearing stress, but with the same level of stress everywhere. So it's still the assumption of a uniform stress distribution. If we were to look at the end view of a round bar, there's my attempt at a circle, we have stresses that are on this cross section, all of the same value. So again, an average shearing stress calculation. Now it turns out that that calculation is fairly easy to do, but it's not always representative of what goes on in a component. Shearing stresses are not usually uniformly distributed, but this formula is going to help us for now. We're going to make things a little bit more complicated a little bit later on. So what we're going to do next is we're going to go through some examples of how to use this formula to calculate the average shearing stress. All right, so for our first example, I've gone ahead and sketched it up. We're going to find the average shearing stress based on our formula, the shear force divided by the area in shear for the situation I have illustrated below. We have a steel bar that's embedded into a concrete cylinder. It's kind of like a fence post. I've drawn it on its side, but we're trying to pull that steel bar with it has a 1-inch diameter out of that cylinder, out of that concrete. All right, so this is our concrete cylinder here. And this is our steel bar. Now, anytime you have shear, it's where you have two surfaces that want to slide past one another. The example I like to give at the beginning of most classes is I bring my scissors into class, and I talk about how another name for scissors is a pair of shears. The cutting action of the scissors, those two blades sliding over one another, is what you should think about when you have a situation of shearing stress. Now, in this particular example, switch to a different color. In this particular example, it's the surface between this steel bar and the concrete that want to slide over one another. So we end up with shearing stresses on the outside or the lateral area of this bar. Let me draw this as a separate picture. There's where it's dashed and embedded into the concrete. Here it is sticking out to this other side. And we have a 1,000-pound force right here. And again, my shearing stresses are on the outside of the steel bar, and they go all the way around the circumference of the steel bar. The concrete is trying to keep this inside the concrete, but the steel wants to be slid out. So you have opposing forces giving us some shearing stresses. Now, to calculate the average shearing stress, it's fairly straightforward. Our average shearing stress in this case is going to be our force that causes the shearing stress, 1,000 pounds, divided by the area in shear. Now, the area that we're talking about has a shape of a cylinder. And the way that we can find the area of that is the circumference, pi times d, times the length that it's embedded in the concrete. It extends over 3 inches. So this would be the value of the average shearing stress. Now, we did talk about resultant forces, and you can get resultant forces from shearing stress distributions as well. If the outside area is area A, and we knew what the value of the average shearing stress was, then the force would be the average shearing stress times this area A. But even if this is a non-uniform stress distribution, I can figure out what the resultant force is by doing an integral. And so we can do an integral over the area of tau dA, but I know what it has to be in the end. It has to be equal to 1,000 pounds because this object has to be in equilibrium. The resultant force, and I'll dash that in, from the stress distribution, no matter how we calculate it, better be 1,000 pounds. All right, so here's one example of an average stress in a bar. It's a pretty straightforward calculation, force divided by area. Let's see if I can do another example. Take a moment, I'll set this up on the next page. Okay, so for this example, we have a punch that has a 500-pound force that's trying to go through a material that's a plate that's 2 inches thick by 5 inches wide. And that punch extends the entire length. Now, so this object is sitting on top of this other plate. And so it's pretty easy to identify the force that we're looking at. It's got 500 pounds on it, so that's going to be on the top of that equation. But next we need to figure out what area in shear. And if we think about this, this would push through, and if it were to go all the way through this material, there would be a plane on the left side and a plane on the right side, all the way down to here. Where the portion of the material under the punch wants to slide down, and this portion of the block on the left and far right sides wants to stay where it's at. So the area that's in shear in this problem would be 2 by 5. And we would have one on the left side and one on the right side. So I'm going to add to it another 2 by 5. And so down here, altogether, the units are inches squared. Now notice there's no contribution to the shearing area on the extreme edge of this block in this section right here. In order to have shearing stress, you have to have two surfaces that want to slide past one another. Although this section right on the side, maybe I can use a green or something like that, although this area here is going downward, there is no other area on the other side of it, so we can't get any shearing stress there. It's a free surface. All right, let's do a couple more examples. We'll take a look at some bolts. All right, and the first joint we're going to look at is a bolted joint. This is called a lap joint. It's kind of like if you were to take two sheets of paper and overlap them just a little bit and run a staple through it or a bolt. If you're looking at sheets of metal, you can get this kind of joint. What we want to do is we want to find out what the average shearing stress is in the bolt. So again, we're going to apply our F over A formula. Now, before we get into those details, I want to talk about how I drew this joint. If you notice, I left a gap between the upper and the lower sheets. This would be kind of a loose joint or a sloppy joint. What I'm doing is I'm finding the worst case situation for the bolt. Now, in reality, you probably want to snug those up together and let some of the friction in between the sheets take some of the load off of the bolt. But if we look at the worst case for the bolt, then it's when we have this loose joint. So in this case, see if I can draw it in 3D. If I look at this particular section and think of it as a very small section, and I'll exaggerate this height so we can see it. Up on top, part of that cross-section area wants to go to the left, and on the bottom, part of that cross-section area wants to go to the right. So the average shearing stress on our bolt in this case is going to be our force divided by a single cross-sectional area, pi over 4 d squared. Now you don't count the area twice in this picture. There's just a single plane where you have opposing forces. This particular joint is called a single shear lap joint. Single referring to a single cross-sectional area. Well, let's look at another joint that's in what's called double shear. Take me a moment to sketch this up. But this joint is going to be kind of like what you might see in a trailer hitch. You have a yoke, and inside this yoke you'd put the tongue, and through this whole assembly, it's hard to draw straight on this, through this whole assembly you'd put some sort of bolt. Now for the thing to be in equilibrium, we'd have a net force F this way and a net force over here going to the right being the same. And we want to find out what the average shearing stress is in the bolt in this situation. Just like we had before, the average shearing stress is going to be the shear force divided by the area in shear. If this force was 1,000 pounds, then we'd have 1,000 pounds divided by the area in shear. Now, we have to be a little bit more careful now. In this particular problem, this bolt, and again I'm exaggerating these gaps, but this bolt on the top wants to go to the left. Just below that it wants to go to the right. And down here, we have just the opposite. The top wants to go to the right, the bottom wants to stay to the left. So in this place, we actually have two sections of the bolt that are in shear. This bolt we would say is in double shear, and we would find that area, the total area then would be 2 pi over 4 d squareds for the bolt. The bolt has diameter d. So this would be a case of a double shear joint. Now on an exam, I would expect you to know if I write down double shear, what that means to do, and then if I were to give you a picture of a joint that looks something like this, you should know how to handle double shear as well. Okay, last thing we need to talk about average shearing stress calculations, and we can get into some more advanced topics in shearing stress. And that is what to do if you have a structure like the one I'm going to sketch here, maybe a simple structure like an L bracket or a truss member where you have some force. Maybe there's a wire over here and then a pin support in this location. Draw that pin support like this. And we might want to find out what the shearing stress, the average shearing stress, is on the pin at this corner. Well, this is where we do our statics. We would draw a free body diagram of that L bracket. If there's a wire, then that's a 2-force member. And as this gets pulled down this way, off at some angle, let's call that angle alpha, then we would introduce tension in that wire. And then typically what we would do is have 2 forces as a horizontal and vertical reaction at the pin. Maybe that's position B, so we'd have a force BY and a force BX. Now with our statics, we can do the summation of moments about point B, and we can do the summation of forces in the X and Y direction, and you can find all of your unknowns if you know the dimensions. So you can find BX, BY, and FY. And let's say this is dimension D1, this is dimension D2. All right. If we want the average shearing stress in the pin, then we know it's the shear force in the pin. I'm using the symbol V for my shear force divided by the total area in shear. And we know now about single shear and double shear, so that area could change depending on what case that is. But we might be interested in finding out then, we need to find out what to use for the shear force. And it looks like we have 2 shear forces down here, BX and BY. You don't want to use just BX or just BY. What you want to use in a situation like this for planar statics is the resultant of those 2 reactions. So in this case, our shear force B is going to be the magnitude, it's going to be the square root of the sum of the squares of those reactions. All right. Well, let's talk a little bit about the equilibrium requirement for shearing stresses, and this statement will make sense here in a couple minutes, I hope. So what I have is a plate that's just sticking attached to the ground. I'm putting a shear force on top of it. And what I've drawn on that plate is a square. Now the square has dimensions delta x by delta y. They're the same thing, but I want to keep those distinct for right now. I've drawn that in red. It's not a hole, but it's actually just a square drawn on that. And on this object, I can cut a free body diagram away. And I can redraw from the top of this shape down to the bottom, and that's what I'll do in this picture. I'll try not to draw it with a jagged top, but here I have that line goes down to the ground. And I want to draw this in a little bit of a 3D perspective, where I have a little bit of a thickness to this plate. And I'm just going to call that thickness T. Now my red box is still on here. I'm going to draw that in. And we can make it like a cube or a parallelepiped that goes all the way through the thickness, so we have that top surface there as well. So here's the dimension delta x, here's the dimension delta y, and there is my thickness T. Well, I know by taking this shear force, dividing it by the entire area of this section, I can find the average shearing stress on the top of that red plate, square on top of that plate. On a side view of this picture, if I were to draw that red square out to the side, here's my shearing stress on the top. And if I were to take and cut it on the bottom, I would get the exact same shearing stress going the opposite way on the bottom. I don't think it's too difficult to tell then that the shearing stress on the top and the shearing stress on the bottom is the same. But let's show you by looking at a little block of forces that does work out. So this is dimension delta x, and this is dimension delta y. Now this is the stresses on the square. We're going to convert that into forces on the square. If we have an average shearing stress, we can take and multiply the stress times the area to get a force. So we have a force on the top, and that's going to be equal to my shearing stress on the top times the area that I have here. And that area is going to be, in this case, delta x by dimension t. My force on the bottom is going to be my shearing stress on the bottom times delta x times t. And because of equilibrium, summation of forces in the x direction has to be equal to 0. The force on the top minus the force on the bottom is equal to 0 will lead me to the shearing stress on the top times delta x times t equal to the shearing stress on the bottom times delta x times t. And the delta x and the t can cancel out, and that will show me that the shearing stress on the top of this shape and the shearing stress on the bottom is the same. Now, we have a little bit of a problem right now, though. If we look at this shape over here, this object is not yet in equilibrium. Equilibrium requires the summation of forces and the summation of moments equal to 0 at a point in a structure. So at this location in the structure, we do have the summation of forces equal to 0. In the x direction, those two cancel out. In the y direction, we don't have any forces right now, so we're covered there. But as it stands right now, if this has a finite dimension, this will tend to spin around. We have a force couple system. In order for us to keep this in equilibrium, we're going to have an opposing force couple system. So in addition to the forces that are on the top and the bottom, we're going to have forces that are on the side. Those forces on the side are going to have to be equal to each other to maintain the summation of forces in the y direction equal to 0. And we're going to have to figure out what to do to get this to be an opposing force couple system. So let's say the middle of that block is point O. If we do the summation of moments about point O, we have one force couple system that will be the force on the top times delta y, and opposing that, I guess this would be a negative if I put my positive directional rotation that way, and opposing that I'd have a positive force on the side times delta x. Now, just as we had stresses from the force on the top, we're going to have stresses from the forces on the side. And I'm going to sketch them in here like this. They go the same direction. that the forces do on those sides of the block. And in the same way, the forces on the side are going to have to be the shearing stress on the side times delta y times T, the area into the face this way. Okay. So if I put these things together with the stresses, moving this to the other side, I have my force on the side, which is the shearing stress on the side times delta y times T times the delta x that I had already written down. That has to be equal to the shearing stress on the top times delta x times T times that distance delta y. And if we notice, there's a delta x, a T, and a delta y on both sides of this equation. So what this tells me is that for equilibrium, I need to have shearing stresses that act as a pair on the top equal to shearing stresses that act as a pair on the side. This is going to be very important for us later on in the semester. What this is saying is that shearing stresses always act as a set. When we have equilibrium, they're all going to be equal to each other, and they point in these kind of corners. They oppose each other. We're always going to have two pair of shearing stresses in this class. All right, just a couple more topics to finish up our discussion of shearing stress and shearing strain now. We know that strains are a measure of deformation. In particular, shearing strain is a measure of angular deformation. Let's think about what happens if we were to take that square that I had drawn on that object on that plate and see what it would look like when it gets deformed. So before it's deformed, it's a square that has nice right angles. I set it up to be a square. And 90 degrees is a right angle, or I can say that 90 degrees is pi over 2 radians. And after this thing gets deformed, it will tend to turn into a diamond shape. I'm going to exaggerate this deformation a lot. But this angle, say in this left corner on the bottom, is no longer pi over 2 radians. It's a new angle right now. It changed angle. The way that we're going to define shearing strain is with the symbol gamma. We're going to define that as the change in angle from pi over 2 radians. Essentially, in this picture, that would be the shearing strain gamma. So if we express this in radians, radians are unitless, and this gives us goes along with our unitless measure for extensional strain. Just like extensional strain, we could have positive or negative shearing strains. Obviously, if the angle decreases, we have a positive shearing strain. Let me say it this way: if theta star is less than 90 degrees, or pi over 2 radians. And if the angle opens up, then we have a negative shearing strain. So at these two corners, we would get the same value, and that would be a positive shearing strain. On these opposing angles, those angles open up, and we would have a negative shearing strain at those corners. Now, something that we talked about earlier was extensional strain and axial normal stress, being very concerned about the sign of those. And that's because most materials, some materials do care whether they're in tension or compression. However, most materials don't necessarily care whether you shear them up or shear them down. It's still those opposing surfaces. So at this point in the course, we're mainly going to be interested in the magnitude of the shearing strain and the magnitude of the average shearing stress. The sign of the shearing stress will be important to us later, but it does depend on how you set up your coordinate system. There's a way that you can find shearing strain experimentally if you wanted to. Experiments have been done where people take and draw a grid on a component and then load it up, and you can measure these dimensions. A common set of dimensions is delta S in L for the sides of this triangle, and you can see from this picture then that the tangent of gamma is equal to delta S over L. The strain values that we're looking at so far have been very small numbers, something times 10 to the minus 3, something times 10 to the minus 6. It turns out that if you take a tangent of a very small number in radians, that is approximately equal to that number. So the tangent of gamma is approximately equal to gamma, which is approximately equal then to delta S over L if gamma is much less than 1. If you have large shearing strains, you cannot do this approximation. You have to leave it in terms of the tangent. But for small deformations, then we can make this approximation. And to finish this up, we're going to talk about the shear stress strain curve, and it's similar to our axial stress strain curve. You can go down to the lab and do a torsion test, and in that test you can apply a shearing stress and measure a shearing strain. The behavior of the shear stress strain curve is fairly similar. It has an initial linear portion, and then it curves over for most engineering materials. And we can identify some particular parts of the shear stress strain curve. Just like we had for stress strain and tension, we have a proportional limit, stress, and shear. It's the highest stress before it gets into the curvy part of the stress strain diagram. We had an elastic modulus E for the tensile stress strain curve. Now we're going to use the symbol G for the slope in the straight line portion. G is called the shear modulus. It's only good when you're below the proportional limit stress to relate stresses and strains. And for this case, we can use Hooke's law in shear, which is similar to Hooke's law in tension, except instead of sigma is equal to E epsilon, we have tau is equal to G gamma. And finally, we can get up here to some peak or ultimate shearing stress. It's the highest point on the shearing stress strain curve. All right, that'll do it for this time. Next time we're going to get a start in on some design topics.